Today we'll discuss about other types of current mirrors or sinks. Two most important current mirrors with feedback are one is Wilson current mirror, the other is regulated cascade current mirror. Both will have feedback, that is negative feedback is included in these circuits so that they will give stable output currents for wide voltage swings and enhanced output impedance. So increased output impedance and stable output currents are going to be results from these two things compared to simple current mirror and cascade current mirror where there is no feedback. First we will discuss about Wilson current mirror. The circuit diagram of Wilson current mirror is shown like this. It will be consisting of four transistors M1, M2, M3, M4 and M1 is separately biased with V bias. So V bias is going to be biasing voltage which is used to bias the M1 transistor and V bias is a fixed voltage. So whenever V bias is fixed, ID1 is going to be the current that is flowing through this one which is also constant, and that current is flowing through M2 and M3 and M4 are going to be other transistors. M3 is diode connected transistor, M4 is going to be simple output transistor. We will see the operation later. First we will see the important points related to Wilson current mirror. Wilson current mirror is going to be having negative feedback. Because of negative feedback, drain current is stabilized. And in this one, negative feedback is nothing but there are four different types of feedbacks are there. One is voltage series, voltage shunt, current series, current shunt. Out of that one, current series sampling is going to be used in Wilson current mirror. So series sampling is used. Whenever series sampling is used, output impedance is going to be increased by 1 plus A beta times, so that output resistance, output impedance is more than without feedback. So this is simple current series feedback which you already learned. Whether the feedback is present or not, that we will first check up. Existence of negative feedback in Wilson current mirror. As we know, Wilson current mirror is provided separately biased with V bias voltage for M1, that is V bias is fixed so that a fixed biasing current of ID1 is flowing through M1 and I0 is going to be the current that is flowing in M4 and M3 transistors, and we are naming separately the currents flowing through each transistor ID3, ID2, ID1, I0. Simply I0 is equal to ID3. First, there is a feedback or not first. So M3, look at the transistor M3 which is diode connected transistor. Diode connected transistor is nothing but whenever gate and drain are shorted together, at that time that transistor is treated as diode connected transistor. So whenever it is diode connected transistor, definitely it will be in saturation. So no need to provide external biasing, it itself provides bias. So that definitely there is a current existing diode connected transistor. So ID3 flows. Whenever ID3 flows, M3 and M2 form a simple current mirror whose VGS voltages are going to be same, so that this ID3 is now making an equal current to flow in M2, so that ID2 flows. ID2 is simply equal to ID3. ID3 is comes in the output side whereas ID2 comes in the input side. So now output current is going to be influencing the input current. Whereas previously if you look at cascade current mirror, the diode connected transistor is at the left side, that is on input side. Output side is going to be simple transistors. In this case the diode connected transistor is on output side, so that this senses the actual current and that will be making a mirror current in the input side, so that it is opposite case, and output current is going to be making influence on input current. So a part of output is making input current, so that is nothing but feedback. A part of output is going to be feeding back to input side. So in the same way, output current is making rise to input current. So the same thing, M3 is in saturation and it senses a current ID3. Since M2 and M3 transistors are identical with same VGS, a current ID2 flows. Current ID2 flows in M2. Here the output transistor M3 producing an equal current in M2, which is nothing but feedback action. Now, how I0 is stable? Again is the variations in output voltage. The principle of current mirror is nothing but it has to provide mirror output with respect to reference current or multiples of reference current at the output, irrespective of output voltage across the current mirror. So even though output voltage is going to be changes, the output current should be stable. This is the principle of current mirror. So how far it is stable across the variations in output voltage, that we will see. As V0 increases, when output voltage try to increase, which causes I0 to increase. Why I0 is increasing when V0 increases? Because of channel length modulation. Even though you are applying same gate to source voltage, whenever more drain to source voltage increase, more drain to source voltage applied, that results in more current. For the given gate to source voltage, as VDS increases, drain current increases. This is the principle of channel length modulation. So, because of channel length modulation, whenever V0 increases, I0 will increase, which makes ID2 to increase. Which makes ID2 to increase. Whenever ID2 increases, at that time VDS2 reduces. VDS2 is nothing but voltage at point A. So voltage at point A reduces. This voltage at point A is nothing but gate voltage of M4. So that there is a reduced gate voltage applying for M4, which causes I0 to reduce. So whenever I0 increases, that will be compensated by decreasing I0, so that I0 is going to be stabilized. Remember the only one important point. Whenever ID2, the current flowing through M2 is going to be increases, why VDS2 is decreasing? When ID2 increases, why VDS2 decreases? That is very very important. Now we'll consider this statement. Whenever I0 increases, that causes ID2 to increase, but that ID2 is going to be biased by the M1 transistor, which is always providing a constant current. So ID2 cannot increase. But in effective, we have to say increased ID2. That implies nothing but that forces drain to source of M2 transistor to reduce. Drain to source of M2 transistor is reducing, and the same current as previous it is flowing in the transistor. That is, now you are getting equal current as previous at reduced drain to source voltages. That is nothing but increasing drain current. So previously, let us assume VDS is equal to 5 volts. Previously you are getting 10 microamperes. Now you are getting same 10 microamperes at 4 volts. That is nothing but for lesser voltage you are getting more current compared to previous case. That is happens. So as V0 increases, I0 increases, I0 increases, ID2 increases because of current mirror action, and whenever ID2 increases, VDS2 decreases because ID1 is constant. Since ID1 is constant, VDS2 decreases. That implies nothing but gate voltage for the M4 reduces. That makes I0 to reduce. So stabilization in I0 results. Next, we will consider output resistance of Wilson current mirror. How to calculate output resistance of Wilson current mirror? As we know, every current mirror is having three important parameters. One is nothing but current ratio, output current to input current. Second one is output resistance. Third one is V0 minimum required. Now we are coming for the output impedance of Wilson current mirror. Output impedance can be calculated by drawing a small signal equivalent of the Wilson current mirror and applying a test voltage across output terminals, which causes a test current to flow in the circuit. Get the ratio of test voltage and test current. So that will give the output impedance. For that one, we have to draw the small signal model of Wilson current mirror. Before drawing the small signal model, we will consider just two important points. We can replace M1 transistor with a resistor value, since M1 is biased with a constant voltage, that is giving constant biasing current, so that makes VDS of the transistor to be constant. So a constant VDS, a constant current, a constant VGS, all the things are going to be constant, so that will be modeled as a single resistor of value R01, that is M1 can be replaced with a resistor R01. Next, a diode connected transistor, that is M3, which can be replaced with equivalent resistance of 1 by GM3. So now replace M1 and M3. So this is equivalent circuit. M1 is replaced with R01, M3 is replaced with 1 by GM3, and VDD VSS act as ground for AC analysis. And this is the equivalent circuit at first step. And for this one, we have to apply a test voltage and test current we will get. Now the rest of the transistors is M2 and M4. Replace M2 and M4 with equivalent models. While going for M2 and M4 equivalent models, consider, is there any body effect present in M2 or M4? M2 source is connected to ground, that is nothing but source and substrate are both are at the same potential, that is ground. So M2 doesn't have any body effect. But M4, source of M4 is not connected to ground, it is at point B. So there is a body effect present in M4. While modeling M4 with small signal model, we must consider body effect also. Generally, body effect increases threshold voltage. So if we consider body effect at that time for the given VGS, you will get less current compared to without body effect case. So drain current, effective drain current reduces when body effect is considered. That is what modeled with an opposite arrow compared to actual drain current direction. This is the actual drain current GMVGS, and this is the drain current which results because of body effect. Both are in opposite directions, so that this current subtracts from GMVGS4. The effective drain current is lesser than GMVGS4. That is previous case. This is without body effect, and this is nothing but effective drain current is with body effect. To say that when drain current reduces with body effect, the body effect current source is taken opposite direction, and simply replace M2 and M4 with equivalent circuits. So while drawing equivalent circuit, identify point A and point B and draw accordingly. Resistor R01 is from point A to ground, so this is point A and this is point B. Point A, from that one R01, so point A to ground, there is a R01, and this transistor is modeled with a resistor R02 in parallel with current source. So that R02 is from point A to ground. So R01 and R02 will get in parallel, and there is a current source in parallel with, that is GM2 VGS2. And between point A and point B, there is a voltage source of VGS4. So point A and point B, there is a VGS4, that is what indicated. This is point A and it is point B, VGS4. And from point B to ground, there is 1 by GM3 resistor. Point B to ground, 1 by GM3 resistor. It is modeled as R03 parallel 1 by GM3. Effectively it is 1 by GM3 only. Okay, this R03 can be neglected, simply 1 by GM3 since it is diode connected. And M4 is modeled with effective drain current along with resistance R0 4. Why current source GMB4 VSB4 is considered for M4? Why the direction is opposite? Just we have discussed the answers for that one. Next, try to write the equations from this equivalent circuit. VSB4 is nothing but VSB bulk. Vs is nothing but source of M4 and bulk of M4. So this is source of M4 and this is bulk of M4. VSB4 is nothing but VGS2. VGS2 is nothing but VSB4. Next, VGS2 is nothing but total current flowing through this resistor. So IT multiplied with 1 by GM3. Next, VGS4 you can write from this one. Write the KVL across R01 parallel R02 and this voltage and this voltage. So there are three terms you will get. VGS4 is equal to minus VGS2 into 1 plus GM2 parallel R01 parallel R02. So next, after that one you can get the equation for the IT and simplify this one, you will get the ratio of VT by IT. All these things are mathematical analysis, you can do it easily. R out is equal to VT by IT. So this is the equation which can be approximated as by neglecting some terms. And if we assume all are identical transistors with GM1 is equal to GM2 is equal to GM3 is equal to GM4 and R01, R02, R03, R04 are all equal, then R out is going to be approximated as R0 plus GM into R0 square by 2. This R0 if you neglect, at that time R out output impedance is equal to GM into R0 square by 2. If you consider cascode current mirror is also having the output impedance GM into R0 square, whereas R out of Wilson current mirror is GM into R0 square by 2. That by 2 is going to be having a less effect, so that they are going to be equal, we can say in that way. So it is similar in size with cascode current mirror. This is how to calculate output impedance of Wilson current mirror. Calculate V0 minimum required. V0 minimum, the meaning of this one, minimum output voltage required to keep both output transistors in saturation. I0 has to be constant. I0 has to be constant only possible whenever both the transistors are in saturation region. So how much minimum voltage we must maintain across M3 and M4 transistors such that I0 is constant. So the minimum output voltage necessary to keep M3 and M4 in saturation is VGS3 plus VDS4 saturation. This is for M3. VDS3 is nothing but VGS3. So that here we are writing VGS3 plus VDS4 saturation. VDS4 saturation is nothing but VGS4 minus VT, which can be written in terms of drain current I. V0 minimum is equal to root of 2I times of beta plus VT plus root of 2I times of beta. This root of 2I times of beta is nothing but delta V, overdrive voltage or effective gate voltage. If identical transistors are assumed, at that time V0 minimum is 2 times of delta V plus VT. So 2 times of overdrive voltage plus threshold voltage. The V0 minimum is same as cascode current mirror. So, and one more thing is V0 minimum is depending on the output current. If output current is increases by increasing the bias, at that time V0 minimum is more. But ideally V0 minimum must be very less. Ideal value is 0. But practically it has to be kept maintain minimum. So we have discussed about checking the feedback in Wilson current mirror and stabilization of output current, calculation of output impedance, calculation of minimum output voltage required to keep output transistors in saturation. In next class we will discuss about regulated cascode current mirror.